Good morning to all of you. Today we will proceed the discussion and complete one very important distribution in statistical mechanics that is quite profound in its usage, and this distribution goes by the name of Poisson distribution. So, today we will discuss this very important distribution in statistical mechanics. So, we have already covered two distributions in the past two lectures, the Gaussian distribution and the binomial distribution. So, today this third distribution completes the set of very important distributions in statistical mechanics, and in one of your upcoming exercise problems we will ask you to show that both the binomial and Poisson distribution in the large and limit reduced to a Gaussian distribution. So, that will be demonstrated in the worked out problems in the assignment sets. So, to begin the discussion on Poisson statistics and hence the Poisson distribution, I would like to take the example of beta decay or radioactive decay. Okay. So, you can think of a material that is decaying such as for example cobalt 60. Okay. So, this would be basically a nuclei which is giving beta particles or electrons as part of the radioactive decay process. So, if you observe a small pellet of cobalt 60 and you wait for, let us say, you wait for 10 minutes, okay, and this is your time axis. Let us say you wait for capital T equal to 10 minutes. Okay. So, this is your time axis, you start here and then you ask yourself a question that in this total 10 minutes or t minute interval, how many minutes did you encounter, how many 1 minute intervals did you encounter. Suppose I make intervals of 1 minute such that you got 4 decays in some interval, and you got the next interval you got 3 decays, and then you got 5 decays, and then you got 1 decay and so on and so forth. Then you got again a 4 decay, then you got 2 decays. So, these are successive 1 minute intervals. In the first 1 minute interval you got 4 decays, the second 1 minute interval you got 3 decays, in the third 1 minute interval you got 5 decays and so on and so forth. So, this goes on, and then you ask yourself a question as to how many 1 minute intervals were observed in the total time duration which gave you 4 decays. Okay. So, this is a problem that can be addressed through Poisson statistics. How many x so, the question is how many 1 minute intervals did you observe with x decays, or let us say m decays, with m decays, m being 4 or 5 whatever. Okay. So, we are saying that two things to keep in mind is that we have taken a 1 minute interval. So, we are asking how many 1 minute intervals are there in the total t duration which have m decays. Okay. So, naturally if you ask the question like how many 4 minute intervals, 4 decay intervals were there, 4 decay how many 1 minute intervals were there with 4 decays? Well, there were finite number of such intervals. If you ask how many 1 minute intervals were there with 5 decays, again you may say okay, there are some finite number of intervals. But if you ask how many 1 minute intervals were there with 100 decays or 1000 decays, well, the answer would be close to 0, because you do not see such large number of decays over a span of 1 minute. Okay, it depends on the radioactivity of the decaying material, but then the answer is known, that if I ask in my 1 minute intervals, if I ask how many 0 decay events were there, the answer will be close to 0, because you will definitely see some decays. If you ask how many 1000 decay events were observed in 1 minute intervals, the answer would necessarily again be 0, because you have a finite duration, you cannot have 1000 decays, okay, in a finite 1 minute interval. So, definitely this is a distribution which peaks at some value and decays at extreme ends. Okay. So, we will develop statistics for such problems. So, let us draw this time axis again, and let us say I am looking for a total time duration of t minutes or t hours. So, big T is my total time duration in some units, okay, and I am observing a radioactive let us say sample which is emitting particles, let us say beta particles or alpha particles, and I am dividing my entire observation duration into small intervals of let us say size dt. Okay. So, I have divided my intervals of a certain width, which is dt, okay, and there are n such intervals. So, the interval number of intervals is nothing but the big T divided by dt. Okay. So, these are the intervals that I have divided my entire domain into. Okay. Now, certainly in each of these intervals there will be some decays. In some interval there will be 5 decays, in next interval there could be 2 decays, in the next interval there would be 10 decays, and so on and so forth. It is expected that there will be very few intervals with no event, okay, because the sample is decaying. So, there will be very few intervals with no event, and there will also be very few intervals with large number of events, let us say 1000 events. I will not see 1000 events in any one such small interval. Okay. So, let us try to make this picture, let us try to reduce this interval delta t further, such that it becomes so small that you have either an event or no event, so small. Okay. So, this is so small that you either have a single event or no event. So, now actually we have made the case so aggressive that we cannot talk about 5 events or 4 events or 10 events and so on. Actually this dt is now so small, okay, I have increased the n, the number of intervals so much that dt has shrunk to such a small width that either you get an event or no event. So, this is in my hand, this construction is in my hand. Okay. I have a total time duration t, and I simply decide to slice this time duration into widths such that the widths are so small that you either have one event or no event. Okay. So, this is in my hand, I have done that construction. Now, look at this, what I have ended up with this beautiful construction, that I have made a Poisson problem actually a binomial problem. So, you even have a event or no event, there are only two possibilities now. So, this careful mathematical construction of this interval has converted my problem temporarily into a binomial problem. Okay. Now, in the binomial problem you know that the probabilities which are only for the event or no event. So, if I say that the probability of getting an event is p. Okay. So, this p would be proportional to the length of the interval, okay, because if I keep the interval dt to 0, then I will not see any event. So, the probability of seeing an event in the interval dt is 0, and if I increase this dt a little bit, the probability of seeing an event increases. So, I already know that this probability of seeing an event in my small interval dt has to be proportional to the width of the interval. So, that is what I have written, which implies that I can write down my probability of seeing an event as some alpha times dt, okay, where alpha has to be interpreted as mean event rate, right, because I have taken a linear interpolation of the idea that if there are alpha events happening per unit time, what is the probability that I will see an event in a time interval dt, then you will simply say that it is alpha times dt. Okay. So, this alpha is a mean event rate. Now, naturally you can ask yourself a question and it is immediately answered. The probability of not seeing an event if I take it as q, then q has to be automatically 1 minus alpha times dt, because I know that the probabilities are well behaved, because p plus q has to be equal to 1. Okay. This condition has to be satisfied. So, we have this condition that the probabilities are well behaved. So, if p is alpha dt, then q must be 1 minus alpha dt, because p plus q has to be 1. Okay. So, then we simply carry over our concepts from binomial statistics. See, the process has been cleverly or aggressively transformed into a binomial problem. So, from binomial statistics I know already that the characteristic function or the generator of moments is given as e raised to minus I k into p plus q to the power n, okay, if there are n intervals or for n events, for n intervals. This is the result that I am simply carrying over from binomial statistics, that is the result that we derived in the last class. Okay. Now, if you plug the values of p and q that we have just obtained, this becomes e raised to minus I k, the value of p that I have just obtained is alpha times dt, plus the value of q, which is the probability of not seeing an event, is 1 minus alpha into dt, and the entire thing is raised to the power n. Okay. Actually, I know what is big N. The power n is nothing but capital T over dt, as defined here. Okay. So, please make note of this construction. Okay. So, replacing this big N by T over dt, we will do that in the next step. So, inside the bracket you can already see a few things can be taken as common. So, I am going to take 1 plus alpha into dt as a common factor, and then take e raised to minus I k minus 1. The entire thing has to be raised to the power t over dt, because the number of intervals is nothing but the total interval size divided by the width of small intervals that you have. Okay. Now, we know that this is much larger than 1, for the simple reason that I have taken dt to be very small. If I take dt to be very small such that there is either an event or no event, the number of intervals has to be very large. Okay. So, if your power is very large, you can expand it using binomial expansion and write this as e raised to, you can write the entire thing as e to the power t times alpha into e raised to minus I k minus 1. Okay. So, the small interval dt cancels off. What I have done here is basically the following. If you find this slightly troublesome, recall that if you have an expansion like this 1 plus x to the power n. Okay. So, in this case my x here is basically this entire thing. Okay. And n is t by dt. So, I can write down this 1 plus x to the power n as 1 simple binomial expansion 1 plus n x plus n into n minus 1 into x square by factorial 2 and so on. N into n minus 1 results from the combination NC 1. Okay. So, and so on. Now, if n is very large, I can approximate this guy as n square and the next prefactor as n cube and so on and so forth. So, this is like an expansion of j going from 0 to infinity x to the power j upon j factorial. Okay. So, in fact, this is this has to be n x to the power j, okay, because n into n minus 1 can be approximated as n square, n into n minus 1 into n minus 2 is approximated as n cube, because n is very large, it is larger than 2, it is larger than 3 and so on and so forth. So, and this is nothing but the expansion of e raised to n x. So, this is what I have done here. So, this entire thing is basically okay. So, you can think of fine. So, now I have the characteristic function in front of me, okay, which is the generator of moments. So, if the characteristic function is in front of me, I can immediately compute the distribution function itself. So, let us keep this important result ready. So, I am going to box it because it is an important result. Okay, so, I am going to sort of keep it handy. Okay. So, let us call this as some give this some equation number. Let us call this as equation 1. Okay. Now, to construct the PDF, okay, the Poisson PDF, I can take an inverse Fourier transform. So, the Poisson PDF for m events in a total waiting time of t interval, okay, with a mean event rate as alpha, is constructed by an inverse Fourier transform. So, I already have a Fourier transform which is the characteristic function. So, this is my characteristic function that is just obtained. And I want to obtain a PDF. So, I must take an inverse Fourier transform. So, the inverse Fourier transform is taken as k going from minus infinity to plus infinity e to the power I k m. This m and that m, the left hand side m are the same variable. I am taking a transform on k, this is an inverse Fourier transform, into e raised to alpha t into e raised to minus I k minus 1. Okay. So, this is my PDF, this is already my Fourier transform, okay, to d of k, fine. So, let us use a different color here. This is my characteristic function. Fine. So, if you, this was just to give you an alert. So, if you do not want to write it like this, I am going to remove it. Now, you can solve this further. It is a very simple exercise. You can immediately see that e raised to minus alpha t. So, I am going to take e raised to minus alpha t outside because it is not a function of k. So, e raised to minus alpha t comes out of the integral. What I have is just k going from minus infinity to plus infinity, e raised to I k m into e raised to alpha t into e raised to minus k, fine, dk. Okay. And this can be written further as so, I am going to write down the second exponential as a summation. Let us take a summation on j going from 0 to infinity alpha t to the power j into e raised to minus I k j divided by j factorial dk, fine. And let us simplify this further. I can write this as integral k going from minus infinity to plus infinity. Now, we can see that I can take out the summation, okay. So, I can take out the summation because the summation is on j and the integral is on k. So, I can rewrite this by pulling the summation outside the integral, okay. So, I am going to pull the summation outside because it is on j whereas the integral is on k. So, everything that involves only j and not k I am going to pull outside and I will take the integral inside the sum. It is a small manipulation that I have done to make things easy for me. What is left over inside is e raised to minus I k j, okay. this j that is inside the integral is summed over outside. Let us reduce this further. We can say this is summation over j alpha t to the power j upon j factorial into 1 upon 2 pi integral k going from minus k to plus minus infinity to plus infinity e to the power minus I k into j minus m d of k. Now, this integral inside is should remind you of a special function, in the sense that this function is called as a Dirac delta distribution on the argument j minus m. Okay. So, this is a Dirac delta distribution. Sorry, okay. This is a Dirac delta distribution. So, this is now reduced to 0 to infinity alpha t alpha times t to the power j upon j factorial into Dirac delta function or Dirac delta distribution on j minus m. Now, clearly you have infinite number of j's, and the prefactor alpha t to the power j upon j factorial well is a function on j that is weighed in this Dirac delta distribution. So, the entire summation has the enormous weight or entire weight coming from the function evaluated at j equals to m. Okay. So, this integrand or this summand is evaluated at the source of the Dirac delta distribution, and this is where it picks up its entire weight. Okay. So, the function alpha t to the power j upon j factorial is computed at the source of the delta function, and which gives me alpha t to the power m upon m factorial. The left hand side was my Poisson distribution P m, probability of seeing probability of observing or seeing m events in a duration of t with mean rate alpha. This is how you interpret your final answer. So, I have a duration t. This t is not the big T that we are, it could be any t, it could be 1 minute, 2 minute, 3 minute, you design, it is in your hand. Okay. So, if you have an alpha which is the mean rate, and then you ask yourself a question, what is the probability of finding m events in a time duration of t? Well, this is the answer. So, you can use this result to compute your probabilities for an event that is obeying Poisson statistics. Now, how do you know that an event is obeying Poisson statistics? Well, the simple answer is that the successive events are completely uncorrelated or random. So, a beta decay is a process which is random. So, it is not correlated. So, a beta decay that is happening now is not related to a decay that happened before, just a moment before. Okay. So, these events are completely independent of each other, and the probability of observing an event is proportional to the time of observation. So, these two things will make the statistics Poisson like, and you can use this Poisson distribution to get an idea as to what is the probability of seeing m events in a duration that is entirely fixed by the observer, which is u. So, now let us call this as equation 2, and I am going to just for the benefit of all of us, I am going to pull this characteristic function right below it. So, let us pull this. So, look at this. So, you have the distribution in front of you, and you also have its Fourier transform, which is the characteristic function. And together these two expressions, beautiful expressions, give you everything that you require for Poisson statistics. For example, if you want to ask what is the mean of the, what is the first cumulant of m observations. So, if you want to see m observations and you want to find out what is the first cumulant, which is basically nothing but the mean itself, well then this is nothing but you can simply compute the generator of cumulants. So, from here you can compute the generator of cumulants, which is nothing but ln of p of k, and that is nothing but alpha t into e raised to minus I k minus 1. So, this is another important result. You have everything now. You have the distribution, you have the you have the distribution, you have the characteristic function, which is generator of moments, and you also have the logarithm of the characteristic function which is the generator of cumulants. Okay, so, you will get your moments from here, and you will get your cumulants from here. So, the first cumulant can be constructed from the procedure that we have discussed in the last class. It is nothing but the first derivative of the cumulant generating function evaluated at origin, which is nothing but, if you look at the expression for ln p of k, this is nothing but alpha times t. Okay. Because e raised to minus I k's derivative is e raised to minus I k, and taken at 0, this becomes 1. But not only that, if you compute the second cumulant, which is the second derivative of the cumulant generating function taken at k equals to 0, well this also comes out to be alpha t. So, this tells you that all cumulants of any order, suppose nth cumulant if you take, which is nth derivative of the cumulant generating function, comes out to be alpha t. So, this is a beautiful result that all cumulants are same for the Poisson statistics. Now, if that is the case, you can construct moments straightforwardly. So, the first moment is just by our graphical computation is nothing but the first cumulant, and that is alpha t we have just obtained. Okay. Let us compute the second moment. Well, this is we need 2 dots. This is nothing but 2 dots disconnected and 2 dots connected. No other possibilities are available. The first case is second moment. Okay. So, that is the first case is first moment square, which is alpha t square, okay. And then you have the second cumulant, which is alpha t. Okay. Then we have the third moment. For this I will take 3 dots, but for 3 dots I can use 3 disconnected dots plus connect 2 of them, leave the third guy. There are 3 such cases, plus connect all 3 guys. And what is this? Well, 3 unconnected dots is nothing but the first moment to the power 3, okay, plus 3 times second cumulant into first moment plus third cumulant. This is nothing but first moment is first cumulant. So, this is nothing but alpha t to the power 3 plus 3 times second cumulant is alpha t. So, this is alpha t square plus alpha t that is it, because all cumulants are alpha t's, the third cumulant is also alpha t, fine. So, this is how you can compute all these moments of the Poisson statistics, and on the left side we have computed the cumulants. So, this is work it out, you should be able to find out what these moments and cumulants are. So, this is a nice exercise to gain an understanding of the concepts. So, I suggest you try it out. Okay. Right. So, now at this stage I will sort of discuss an important example, a worked example to demonstrate how to apply Poisson distribution to solve problems. Okay. So, let us take a worked example. Okay. So, I am going to just give you a problem. Let me read out the problem. So, you have a, let us say you have a radioactive source emitting alpha particles, let us say. Okay. And you saw that 1800 alpha particles were observed to be emitted over 10 hours. Okay. And the question here is how many 1 minute intervals, please pay attention, the intervals are 1 minute intervals, how many 1 minute intervals did you observe with no alpha particles? Okay. So, that is the first case. So, I am going to write it as the first case. So, how many 1 minute intervals did you observe with no alpha particles? And the second case is how many 1 minute intervals did you observe with 5 alpha particles? Okay. That is the problem. So, which means if you want to understand this question, it is like you observed it for a total time of 10 hours. Okay. So, you have basically intervals of 1 minute, and you ask yourself a question. So, you saw 1800 events. So, the alpha, which is the mean event rate, is nothing but 1800 divided by 10 into 60, which is 3 events per minute. Okay. So, this is the mean event rate for your problem. Okay. So, then suppose you saw one event here, you saw nothing here, then you saw 6 events here, then you saw 5 events here, then you saw 4 events here, and so on and so forth, completely random. Okay. Now, the question is how many 0 event 1 minute intervals are there. So, you already have the second interval which has no event, but there could be also 1 minute interval here with no event here, and further down the line you may have one more such. So, basically you need to count, you basically asked how many such intervals exist. Okay. So, what you have to do first is compute the probability of observing no event in a 1 minute interval. Okay. And that the answer is simply if you recall your answer, if you recall your distribution, that the probability of m events in a time interval of t is given as alpha times t to the power m e raised to minus alpha t upon m factorial. Okay. So, that is the result that we are going to use. This gives us our m is 0. So, we get alpha t times to the power 0, which is 1, to e raised to minus alpha t. Now, alpha is 3 and our interval t here is 1 minute. Okay. So, this is 3 into 1 divided by m factorial or 0 factorial. Okay. So, this comes out to be e raised to minus 3, fine. This is the probability of seeing a 0 event interval. Now, if your question is how many such events are there, how many such intervals are there, how many such intervals, such 1 minute intervals well, the answer is you multiply the probability P0 of 1 minute multiplied by the total number of minutes, okay, which is nothing but e raised to minus 3 into you had 10 hours, which means you had 600 minutes. So, basically this is roughly 30 minutes. Okay. So, you can check this out by calculator, and similarly if you want to find out how many, so this is the answer to the first part, that there are roughly 30 1 minute intervals where there was no alpha disintegration. Okay. So, we have seen there is one such interval, there is another such interval, there is another such interval. This way there are some 30 such 1 minute intervals where you did not see a alpha particle disintegrated. The second question is straightforward. So, this was the answer to your first. The second question was basically how many such 1 minute intervals with 5 disintegrations happened. So, for that I must compute the probability of getting 5 disintegrations in a 1 minute interval. Okay. So, the answer would be alpha is 3. Okay. So, I am going to use this formula here. So, alpha is 3, the time is 3, time is 1 to the power m, m is 5 into e raised to minus 3 into 1 over m, which is 5 factorial. Okay. So, this is 3 to the power 5 into e raised to minus 3 over 5 factorial. Okay. So, this will come out to be roughly 60 minutes. So, there are basically total 60 such 1 minute intervals where you see that there are 5 disintegrations. So, there is one here, there could be one more here down the line, there could be one more here down the line, so on and so forth, and there are basically 60 such 1 minute intervals where you will see the disintegrations that are, there are 5 disintegrations of the radioactive particle. Okay. So, no, in fact I have just computed the probability. So, let me just I have just made a small error here. So, this is the probability. To compute the number of minute intervals, I have to compute. So, the answer how many such 1 minute intervals exist. I must multiply this with the total number of minutes like I did before. Okay. So, this is 3 to the power 5 into e raised to minus 3 upon 5 factorial into 600, and this will be around 60 minutes. Okay. So, we end here, and we will meet again in the next lecture and proceed with the discussion on many random variables, which is again a very interesting subject.